Welcome to Math 325, Linear Regression 1. During this first week, I want to discuss some of the fundamental results and basic elements associated with simple linear regression models. And to get started and illustrate some of those details, I want to take a look at an example. Suppose a researcher wants to examine the relationship between monthly housing payments and debt level for households in a particular geographic region. Now I have some data, 500 data points, in a Excel file called Payment Data SLR, which I'll make available to you, and we'll use a little bit later in this presentation also. Now, whenever we're dealing with the nature of the relationship between two variables, scatter plot is often, very revealing. And when we do a scatter plot of debt and monthly housing payments for these 500 data points that I have, we notice that there's certainly not a deterministic relationship between debt level and monthly housing payments. But there is a general trend. That is, as debt level increases, it appears that the monthly mortgage payments in general are increasing too. That is, we may have a statistical relationship. And of course, unlike functional relationships, statistical relationships have noise in them. They're not perfect. And so what we want to do is we want to examine to determine whether or not we can apply a statistical model, in this case a simple linear regression model, to debt level and monthly mortgage payment. Now it's very important from the outset to understand that statistical relationships do not necessarily provide evidence of causation. And that goes back to our understanding of the simple, or the, simple correlation coefficient. The correlation coefficient that we discussed in our statistics course. And we know from that discussion that correlation does not necessarily imply causation. So I do want you to keep that in mind as we make our way through our course. So we're going to examine a statistical model, and looking at the scatter plot, we might convince ourselves that indeed there is a linear relationship between x and y. That is, as x gets bigger, y gets bigger, and it seems to be linear in nature, but it's certainly noisy, and so we need to account for that noise. And our model does account for that noise in the inclusion by including this random error term epsilon sub I. Now, we call the x variable a number of different things. Some people refer to it as independent. I don't like that term. I prefer predictor or regressive variable. We sometimes see y as denoted as dependent variable. To me, the terms dependent and independent sort of imply some sort of causation. I don't like them. And as a consequence, I'll refer to the y variable as the response variable in most of what we do in our course. I would urge you to do the same. Now, this random error term, this noise in the model, we're going to make some assumptions about this. We're going to assume that those random error terms are uncorrelated, that they have a mean of 0, and that they have a constant variance sigma squared. Now, at some point, we're going to have to validate those assumptions, and will. But given those, then what we're suggesting is that we have a linear relationship between x and y when looking at the entire population, and the mean values associated with the responses can be found by looking at beta 0 and beta 1. Now, in general, we don't have the wherewithal to know the entire population. If we did, then we have no need for statistics. So typically what we do, given the assumption that there is indeed a linear relationship between y and x, and that it's statistical, that is, it's noisy, then typically what we do is we go out and take a sample. Now notice, these open circles represent members of the population that were not sampled. These green dots on my screen represent the sampled observations. And so if we had these sampled observations, the goal then would be to fit a line to those data points. And the line that we fit to those data points may not coincide precisely, exactly, with the line that governs the mean behavior in the population, the mean behavior of y in the population. And so we know that the line that we generate based on our data is an estimated regression line. It may not coincide precisely with the population model. And that's the essence of statistical analysis. We call that fitted regression line y sub I hat, and the estimators B0 and B1 are estimators of beta 0 and beta 1, and the question becomes, how do we choose the line given a particular data set? In order to help us do that, let's take a look at this thing we call E sub I, the ith residual. That is the difference between the observed values and the fitted values of y. And in order to fit the line, one method that we might use is this notion of ordinary least squares fit. And the ordinary least squares fit says, let's fit the line so that the distances that the points in our sample lie from the line are minimized. So the ordinary least squares says, let's minimize the sum of the E sub I squared. Now notice we don't minimize the sum of the E sub I, because if we fit the line properly, the sum of the E sub I are going to be equal to 0, because we have some that are plus, some residuals that are plus, we have some residuals that are negative, and they will in fact cancel one another if we fit the line so that it goes through those points so that the distance that the points lie from the line is minimized. So we want to minimize this thing called the sum of the residuals squared. We give that another name. We call that the sums of squares error. And we want to come up with an estimated regression line. That is, we want to come up with estimates associated with the estimators B0 and B1 that allow that line to be fitted so that the sums of squares error is minimized. And the question is, how do we do that? Well, our textbook gives us the results. And it turns out that if we let B1 be equal to what you see on this particular slide, now understand there are a lot of different ways to write B1. And B0, if we allow it to be computed based on what you see on this slide, then that fitted regression line will be the line that minimizes the distances that the observed values lie from it. Now notice that B1 has some relationship to the correlation coefficient R sub xy. We got the standard deviation of y in the numerator, standard deviation of x in the denominator. These are terms that I hope are familiar to us from our statistics course. This slide is very important. What it demonstrates is that B1 and B0, those estimators, B1 and B0, are linear combinations of the y sub I. Now, the weights associated with those linear combinations, in B1's case, the sum of the x sub I minus x bar over the sum of the x sub I minus x bar squared, they're a little complicated. And for B0, it's even more complex. But I do want you to understand, because this is going to be critical for us as we discuss inference, that B0 and B1 are indeed linear combinations of the x sub I. Excuse me, linear combinations of the y sub I. It turns out that the expected value of B1 and the expected value of B0 are beta 1 and beta 0 respectively. That is, B1 and B0 are unbiased estimators. We can compute the variance of B1 and the variance of B0, and it's very important to note that the variance of B1 and the variance of B0 are dependent on the variance of the random error term sigma squared. Now, that's a population parameter, and we may not know it either. And so the question becomes, how can we estimate it? Well, it turns out that mean squared error, which is the sums of squares error divided by n minus 2, and we divide by n minus 2 in this case because we are estimating in our simple linear regression model 2 parameters. It turns out that mean squared error is an unbiased estimator for sigma squared. That is, the expected value of mean squared error is sigma squared. And so it's a very good placeholder for sigma squared. And I'll generate a handout that demonstrates the validity of that statement, that mean squared error is an unbiased estimator of sigma squared. It'd be a nice way for you to kind of ramp up. If you go through and look at it, it'd be a nice way for you to remember some things from our basic statistics course too. Now eventually, I think it's in section 1.6, we're going to make some assumptions about these random error terms distribution. And we're going to assume that those random error terms are normally distributed, again with a mean of 0 and a variance of sigma squared. And that's going to have some implications for us, because y sub I then is going to be normally distributed. The y sub I are going to be normally distributed. And since B0 and B1 are linear combinations to the y sub I, they are going to be normally distributed too. We're going to assume this notion of constant variance across all levels of x, that the random error terms are independent, and most importantly that we do have a linear relationship. And we're going to have to validate all those assumptions at some point in time, and will in our course. As I mentioned, if the random error terms are uncorrelated and normally distributed, then the y sub I, which takes their distribution from the random error terms, because beta 0 and beta 1 and xi, they're just numbers. So y sub I takes its distributional behavior from the random error terms. If the random error terms are normally distributed, the y sub I are normally distributed. And if the y sub I are normally distributed, because B0 and B1 are linear combinations of them, then B0 and B1 are normally distributed. And that's going to open up a lot of opportunity for us to make inference and really come to grips and really understand what our estimated regression line provides for us. There's some discussion in our textbook about maximum likelihood estimators of beta 0 and beta 1. Suffice it to say at this point that the maximum likelihood estimators for beta 0 and beta 1 are precisely the same B0 and B1 that we get when we do the ordinary least squares approach. The maximum likelihood estimator of sigma square, however, is biased, and that's why we prefer to use mean squared error. Now at this point, I don't want you to get too concerned about maximum likelihood estimators. We'll talk about that as the course unfolds, but for now, I want you to understand that the estimators that we're going to use are beta 0 and beta 1, B0 and B1 as estimators for beta 0 and beta 1, and mean squared error will be the estimator of choice for sigma squared. Here's a little example. Now look, in our textbook, they go through, the authors go through a lot of arithmetic in order to help you compute estimates B0 and B1. And you should certainly look at that and know how that computations work. But the fact of the matter is, Excel provides all this for us lickety-split, and I urge you to use it. So here's the data set in the Payment Data SLR Excel workbook that I'll make available to you. And there's a number of different variables here. There's 500 observations. I've got location, ownership, income, utilities, and over here in columns H and I, I've got the debt level and the monthly housing payment. And those are the variables of interest in our case. Now, in order to run a linear regression model, in order to estimate a linear regression model using Excel, we go to the Data tab, and when we click on the Data tab, we see the Data Analysis Toolpak out here in the Analysis subsection. If you don't see the Data Analysis Toolpak, then that means it hasn't been launched yet. So you need to go to the Office button, scroll down to Excel Options, and when you get into Excel Options, click on Add-ins. And when you click on the add-ins, you'll see the list of add-ins here. In the Analysis Toolpak and the Analysis Toolpak VBA, both need to be added in. If it's not launched, they'll be down here in the inactive. Just click them, and go ahead to go, and that will launch that add-in. If you don't see the Analysis Toolpak or Analysis Toolpak VBA add-in, then someone loaded Excel in your machine incorrectly, and you're going to have to reload Excel. Supposing that the Data Analysis Toolpak is there, we click on it and we get this dialog box, and you notice that you can do an awful lot of things in the Data Analysis Toolpak. As you scroll down, they're in alphabetical order. One of them is regression. So we hit the regression, hit OK, and now we get this regression dialog box. And it says, okay, where are the response variables? The values for the response variable. And there are monthly payment. So I'm just going to grab them. There's probably a much more efficient way to do this, I'm sure. But I'll just scroll down and get them all. There's 500 of them there. And then I'll do the same for the debt level, the X variable. Notice I grabbed the labels. And they're certainly not numbers, so we're going to have to tell Excel that I grabbed the labels, and I can do that easy enough with this checkbox right here. Now there's some stuff down here that we don't need to be worried about at this point, some residuals, normal probability plots, some confidence level stuff. Don't worry about any of that right now. But let's send the output to a worksheet called output, and when you hit OK, Excel cooks and it generates some output, and that output looks like this. Now at this point, what's important for you to note is right here under this coefficients title. You see the coefficient for the intercept is 441.58. The coefficient for the debt level is 0.1243. Those are the estimates B0 and B1 respectively. And it's really that simple. Now again, you can go through all the arithmetic that's discussed in our textbook. I think you should. You can do the homework associated with Chapter 1, and in some cases you're invited to actually do the arithmetic, but the bottom line, Excel does it all for us. And now the question becomes, how do we interpret the model? And of course, this 0.1243, that's a slope, and it has the same meaning of any slope. It's a rate of change. And in this particular case, what it means is for each additional dollar of debt that a household has, their mortgage payment goes up on average $0.1243. Now the 441.58, it really doesn't have much meaning in this case. And the reason it doesn't have much meaning is because we don't have anyone with zero debt level. If we did, then we might convince ourselves that the 441.58 represents the average housing payment for someone with zero debt level. But we don't have anybody in our data set with zero debt level. And I always am cautious about extrapolating the model, the estimated regression model in this case, beyond what I call the relevant range. We're sometimes forced to do it, but it's a tricky thing. So in this particular case, I maintain that the 441.58 is nothing more than a mathematical artifact, and I don't try to subscribe to it any particular meaning beyond that. Well, that's how we can generate a simple linear regression, an estimated simple linear regression model using Excel. There's lots to do in Chapter 1. I suggest that you read it very carefully, take notes as you go through it, look at some of the handouts that I generate. Certainly do the homework, ask questions, and resolve from the get-go to do your very best in the course and stay on task.